malnutrition, biodiversity, COVID-19, and we get students to investigate that global issue on a local level, engaging in local investigations in their community or within their families, making local decisions about that issue, and engaging in local action to make a difference. We do all of this to help students understand that local actions can have global impact. And through this work, we hope that students will achieve the understanding that STEM education can be used to help them develop a sustainability mindset, one that helps them connect global and local issues, empowers youth to know that they can make a difference through their own actions and agency, that by doing so, that you can help ensure equity for others, and that you also engage in your own self-reflection and remain open-minded so that you keep in mind the perspective of others. So today, what I'm going to do is provide an example of one of our Smithsonian Science for Global Goals modules that's available for free in 25 different languages. And it's called COVID-19, How Can I Protect Myself and Others? So this particular module is based on the following UN Sustainable Development Goals: good health and well-being, Goal 3, Goal 6, clean water and sanitation, and of course, Goal 4, quality education, which we believe undergirds all of these Sustainable Development Goals. COVID-19, How Can I Protect Myself and Others, is made up of 7 tasks, which are all driven by common questions that students ask. And I'm going to take you through those 7 tasks so that you understand how the lessons are structured. And then I'm also going to end the talk by taking you through a set of framework that we use to design the COVID-19 module and all of our guides, so that you could use that, feel free to use that same framework to not only write lessons that integrate STEM education with sustainable development, but also help us engage youth in local action. In task 1 of this module, COVID-19, How Can I Protect Myself and Others? The first thing we do is we ask students, what's happening in the world right now? Because this module is designed for students all over the world, we want to make certain that students have a chance to investigate the scientific issue from their local perspective, but bring it up to a global issue. All throughout the module, we embed emotional safety tips so that we can integrate social and emotional learning into STEM education. We also structure every single lesson or task in the following ways. We divide the lesson into 3 parts. Discover, where students ask questions of themselves and others through surveys of their communities or their family members or their fellow teachers and students. Second, understand, in which we have students investigate hands-on the underlying science of that particular issue. And finally, act. In that portion of the lesson, we have students use their new science knowledge, their new STEM knowledge, to do something with it, to do social good, whether that's engineering a solution to a local problem by designing their own mask, or in a mosquito module, designing their own mosquito trap. In the first task of COVID-19, we also have students learn about themselves. And how do we do that? We have the students develop an identity map. Every one of our modules starts this way, because we believe that in order for students to understand a complex global issue on a local level, they have to understand the perspectives of others. And in order to understand the perspectives of others, they have to understand themselves. So we have students take a simple piece of paper and draw their name in the middle. And then around their name, we have them write everything that they could explain to describe themselves. Some students may want to not just draw their identity map on paper, but we might have them create a physical identity map. In this picture, for example, you see that this student pulled together all of the objects that describe who they are. We help students understand that their identity is not static. It changes over time. Those things that define who you are also change over time. 5 years ago, I wasn't a grandmother. Today I am. And a grandmother would be written on my identity map. 5 years ago, or even 1 year ago, a mask would not have been part of my identity, but it is today. So we help students understand that their identity changes and that we want them to think about who they are so that they can better understand the issues that they face around them. We also have students learn about others. These are 6 scientists or 5 scientists that are highlighted in the COVID-19 module. How can I protect myself and others? We interviewed the scientists and we provide quotes and stories about the scientists all throughout the module so that students can understand that STEM is accessible to them. Some of these individuals are scientists. Some of them are technologists who use data to solve complex problems like COVID-19. Others are public health specialists. So we want them to see themselves in the careers of STEM, especially those who use STEM for social good. In the second lesson or task, we have students answer the question, how can keeping distance from others help? This is where we have students understand the basic protective behavior. And that protective behavior is that virus, SARS-CoV-2, that you see in the very bottom right, that virus is carried by respiratory droplets. And by having students take a simple object, like a phone or a mirror or a glass, we have them breathe into it or on it, wipe their finger along it, and they see that there's water when they breathe, talk, speak, cough. Those respiratory droplets carry the virus, SARS-CoV-2, if an individual is infected with it. And what we want students to know is that that respiratory droplet, if it's carrying a virus, will typically carry around 6 feet or 2 meters. So we have students investigate firsthand through modeling why small droplets of water, respiratory droplets, which might be carrying the virus, only can be carried a certain distance. We have them take a simple bowl or a bucket. They measure a distance from a wall. They do a simple activity of flicking the water onto the wall to model the behavior and movement of respiratory droplets. We integrate math by having them graph that relationship to show that there is an inverse relationship. The further away you are, the fewer droplets will reach the wall that's 2 meters away. We also help students understand data and draw evidence from studies. So for example, in this study, evidence shows that respiratory droplets travel around 6 feet or 2 meters. We want students to associate those water droplets that come out of their mouth and the modeling activity with movement of these small droplets with this associated scientific study that shows that evidence shows respiratory droplets travel about 6 feet or 2 meters. In a task that's called, how can covering our noses and mouths help protect us? Students repeat the activity that they did in the previous lesson, only this time they have a friend or a sibling who they're allowed to be socially distant or allowed to be socially close to, hold up a towel in front of them, and when they flick the water, they see that there's a reduced amount of water that reaches the wall because of that cloth covering. Through this activity, students see that by wearing a mask, you're actually protecting others from your respiratory droplets. In task 4, we teach students the underlying science of the structure and function of the virus SARS-CoV-2 that causes the disease COVID-19. And we have them do a simple activity where they use oil, butter, or ghee to replicate or model the oily fatty substance that exists along the outer area of the virus. We show them that by rubbing, if you put oil on your hands and rub your hands together, it's very hard to get that oil off. If you use water, it's very hard to get that oil off. But if you use water and soap combined together for not 10 seconds, but 20 seconds or 40 seconds, you can get the oil off of your hands. And that's what we're trying to do with students, is help them model and physically understand the reason we're asking you to wash your hands during COVID-19 is the underlying science of the virus's structure is broken up by that soil, soap and water combination. In task 5, we help students understand contact tracing. So why is it that an individual who contracts the virus has to engage in contact tracing? Because of what's called primary contacts. So if an individual at the top of the picture contracts COVID-19 and they have been in contact with 3 individuals, it is possible that they can actually impact 13 individuals, not just 3. Why? Because that one individual at the top who contracted COVID-19 has been in primary contact with 3 people, but they have been in primary contact with 10 additional people or 9 additional people. And that one individual person could actually impact 13 different people. And so that's why contact tracing and testing is so important. So we help students see the underlying math and the technology behind contact tracing with a phone that traces your movement or whether you've been in contact with an individual who's been diagnosed with COVID-19. In task 6, we help them understand that you have to look at the evidence that underlies a claim. This is a common thing in STEM education. So if the claim is that COVID-19 is only spread through large respiratory droplets, but now we have evidence from 239 scientists from over 30 countries who published a letter to the World Health Organization saying that they have strong evidence, emerging evidence, that it's also carried through tiny droplets or airborne transmission, which means that it can be carried further than just 6 feet. So we help students understand, how do you deal with an infodemic at the same time you're dealing with a pandemic? How do you make certain that all the evidence and news that you're getting, you can trust? So we teach them to look at the source. Is it a trusted source of information? What's the evidence to support the claim? And finally, in task 7, we have students bring all of their actions, all of their new discoveries, their new understandings of science together to use that new scientific knowledge to do something that changes their behavior and the behavior of others. In this example, this young boy, and this is a true story, who's in Mexico, what his teacher taught him this COVID-19 module, and in the end, he created a TikTok video that he is dancing to a song, and he changed the words to be about the importance of wearing a mask. It's adorable. So I'm now going to share with you in the last 15 minutes underlying frameworks that I believe you could use in any topic that tries to bring together STEM education and sustainable development. So the first is what we call the Global Goals Action Progression and the lesson structure of discover, understand, and act. So this is our framework, which we call the Global GAP, the Global Goals Action Progression. Our goal is to get students to progress through traditional inquiry-based science education all the way up to acting, with the eventual goal of changing students and helping them develop their sustainability mindsets, as well as their scientific literacy. So the way this framework works is that we believe at the bottom of the framework that every student comes to every classroom with existing learning dispositions. They also come to a classroom with a particular cultural context. A student learning about COVID-19 in Malaysia or Indonesia may look at that pandemic either the same or differently from a student who is in the US. And that cultural context matters. Students also come into our classroom with different background knowledge. And we have to take all of that into account when we begin to educate youth in STEM education for the purpose of sustainable development. As we move up from the bottom of the pyramid or triangle, you see the traditional forms of STEM education, getting students to question and investigate, and hopefully investigate through the hands-on practices of science, technology, engineering, and math. Then we get students to think critically about the issue and to think about that issue not only on a local level, but on a broad systemic level, both locally and globally. And then to take all of that information, synthesize it, develop a management plan, and then act. Do something with your new knowledge. As we saw in that picture of the little boy, he learned that wearing a mask not only protects himself, but more importantly, protects others from his respiratory droplets if he were to have some type of infectious disease like COVID-19. He knew that his job was to help change the behavior of others as well as himself. He developed a sustainability mindset. He became scientifically literate. And now he'll take that knowledge to a new class, a new subject, and now we'll enter that class with a new learning disposition and new background knowledge. You'll also notice that in every single lesson I mentioned that we use what's called the Discover, Understand, and Act lesson framework. And the way that is, what we mean by that is at the beginning of every lesson, if we want to integrate STEM education with sustainable development, then we have to first start by having students examine the social scientific issue that's affecting their local or global communities. If students are learning about mosquito-borne diseases or biodiversity or energy, that it's really important that they understand it not only from a global perspective, but a local one, and use their community to gather and discover that information by surveying others. In the second part of every one of our lessons, we call that the Understand part of the lesson. That's where students examine the underlying science and social science of the issue using their community or their classroom as their STEM laboratory. We have them engage firsthand in hands-on investigations because students will remember that information much longer than if they are told the information directly, as we heard yesterday from many of our speakers. And finally, we get them to use that new scientific knowledge, that new STEM knowledge, to do social good. Whether it is designing something that helps to reduce their carbon footprint or track their carbon footprint, maybe developing an app to track how many times they do something that produces carbon, whether it's designing a mask that helps protect themselves from COVID-19. Some examples of the Discover, Understand, Act framework. Discover, this is where we want to foster conversations. It's what UNESCO calls social outcomes. We want to make certain that students are talking to others, collecting information from others, understanding themselves through identity maps, and understanding others through perspective taking. These young students are using our COVID-19 module in South Korea. The second part of the lesson is what we call Understand, where I told you this is where they investigate the issue using their STEM knowledge. This is what UNESCO calls cognitive outcomes. You can see these students that I showed you earlier engaging in a modeling activity to understand what do we mean by a respiratory droplet and why is 6 feet or 2 meters the recommended distance to stay physically distanced. And finally, the ACT part of the framework, where I mentioned we want students to use their STEM knowledge for social good. This is what the UNESCO calls behavioral outcomes. And we saw that in that little boy who made a TikTok video to share the importance of mask wearing. And I'm going to end with 2 slides that show you what we really is called the SDG, Sustainable Development Goal Action Continuum. It's something that we recently published a paper that I have shared with Rini, that this SDG Action Continuum helps to ensure that all of our citizens engage in what we call extreme citizen science, or what the field calls extreme citizen science. So 2 last slides. The SDG Action Continuum is the belief that action falls along a continuum or framework. Many students engage in what we call executed actions. They are the most basic actions that someone tells you to do to address a problem. For example, if you tell your students, we want you to wear a mask, or if you tell your students, we want you to recycle, and they do, but they don't understand why, that's what we would consider an executed action. Moving a little bit further along the continuum is what we call an informed action. These are actions in which you use facts, investigations, and evidence to determine your action. The little boy who developed the TikTok video was doing what we would consider an informed action. He used his own facts and investigation and evidence to determine an action around mask wearing. Next, the even more advanced actions we call connected actions. Connected actions are where you're thinking through the interconnections between your local actions and your global actions, between the actions of society and the actions of science. And finally, the most complex actions are what we would consider the most desirable, and those are considered actions. Considered actions are the most desirable actions which combine action with reflection. It balances competing interests. Our students can't learn science, technology, engineering, and math in a vacuum. They have to learn that you have to balance perspectives that are not just scientific, but also social and emotional, economic, environmental. You have to balance local actions with global actions. You have to balance systemic inequities with ethics. And these are all what we would consider the most complex actions, which many we're very well educated adults and citizens would engage in, considered actions. And I'll leave you with this. When we believe in bringing STEM education for sustainable development, we are trying to move from traditional approaches to what people call citizen science to extreme citizen science. In other words, when we bring scientific questions to the community, we don't want the community to just collect data, submit it, and answer those questions for us. We want that citizen to engage in extreme citizen science. Our youth are identifying problems within their local communities. They're engaging in changing their behaviors to act, to solve these problems in the service of achieving sustainable development. That is what we would consider the most extreme citizen science. And so I hope that this talk, in which I shared with you the frameworks that we've used to combine STEM education for sustainable development, are frameworks that you can apply in your own local context. Thank you, Rini.
Thank you so much, Dr. Carol O'Donnell. It's a very inspiring presentation, in my opinion. So there is a question that is come from Mr. Aib Saifullah from Universitas Pendidikan Indonesia. This is like a normal school in the past, but they become a university right now. From task 1, we get information about student profile from diagram they make, how this data will contribute to the learning outcomes after students have done the final task. How can we use this data for the consideration of planning the STEAM instruction? Did you get the question?
So I want to clarify, was the question about, for example, the identity map that the students do in task 1?
Pak Aib, could you please text what do you think? If I don't know if you could talk, I hope the operator will give you the.
And Rini, while he does that, I would say that the change in students' thinking between task 1 and task 7, just like in any of our curriculum materials that we have in STEM, we want students to change their knowledge of STEM. We want them to change their, as we said, behavioral outcomes, so their actions. And we also want them to change their social outcomes. So in the beginning, for example, we ask students, what do you already know about COVID-19? And then we have students revisit that at the end of the module. And our goal, of course, is to develop, to demonstrate that we have shown growth in their scientific understanding. But in addition, we also want to see growth in their actions. So at the beginning, we ask students on a scale, this is on a like scale, on a scale of 1 to 10, how confident are you that you can actually protect yourself from COVID-19? Or how confident are you that you can make a difference in mosquito-borne and controlling mosquito-borne diseases in your community? Most of our students at the beginning of our modules say they have very little agency, very little belief that they can actually make a difference. By the end of the module, when we ask the question again, you see extreme growth in students' understanding of the science, their belief in being able to use the science to engineer solutions to problems, and also their understanding that their belief and who they are as an individual actually grows over time.
Mm-hmm. Okay, thank you. I hope your answer can make Dr. Aib Saifullah satisfied because I don't have any response from him from the other room. So
and I'll just add that it's really important in STEM education that we're not just assessing what we would call disciplinary core ideas, like assessing their conceptual knowledge of science, technology, engineering, and math. As you heard yesterday, it's also about assessing their practices. We're in this talk today, I'm just saying, in addition, I think we also need to assess how students use their new STEM knowledge to change their behavior and the behavior of others for social good.
Yeah. It's very interesting for me when you said about the action. There are 4 types of action, and then we have to make sure that our students could develop the considered actions in their life. So if all people have that considered action, our world will be a better place for everyone, right? So
that's right.
I was wondering, how do you think the considered action can be like developed in students since early age? So maybe your lessons already tell us about that, but maybe you can explore it to me,
Yes,
all of us.
It's a great question. And this is what the paper that we wrote focuses on. So what we believe is that in order to shift students' behavior and to get them to use their STEM knowledge for social good and for purposes of sustainability, it is not expected that we would be able to engage our 8 to 17-year-olds in considered actions immediately. It's too complex. And we believe that each of these actions is important, but they do develop over time along this continuum. So as I noted, I think if we have very young children, perhaps ages 6 or 5, and we say to them, it's important to recycle, put your plastic bottle into this bin. And they do that behavior, that executed action, that's great. But over time, if as educators, we help students understand why we're asking them to recycle plastic, or why we're asking them to cover their mouths and noses, and teach them the underlying science, engage them hands-on in modeling behaviors that help them to investigate that particular problem, then I think that they're more likely to move beyond executed actions, as we know it, like to informed actions. Now they know, the more I understand, the more evidence I have around this action, the more likely I am to engage in it. And so along the continuum of 8, for example, 6 years old or 8 years old to up to 17-year-old, the older you are and the more often you've been engaging in this discover, understand, act, the more likely we can develop into adults as adults who engage in considered actions, where we're keeping in mind the balanced perspectives of others and aren't making decisions that use science based on our own individual thinking, but based on how it's impacting others as well.
Okay. That's a very inspiring theme for me. Thank you so much. I hope the same feeling will be felt by others in the room. I was wondering if there are any more questions from the audience. I will check because we still have 2 more minutes. There is the one more from, maybe it's a kind of comment from Kobina, Universitas Negeri Yogyakarta. It's also the same like UPI just now. The previous one, it is a teaching school. Thank you for the explanation. It is very inspiring. I want to know, what do you think when students succeeded to build their understanding, but they found it is practically different when our student found what has happened at home?
That's
so the difference.
A wonderful question. So there was a study done that was published in, it was called In Nature. And the article was written by somebody by the last name of Lawson, Lawson. And that article was about what's called intergenerational learning. And what the article proved was that when you educate youth on climate change or climate science, that those students go home to their families and they have conversations with them. And that this article proved, this was a research study with hundreds of individuals in the sample, and that they showed that when students learned these topics at school, they went home, had intergenerational conversations. That means they had conversations between the child and the mother or father, and that the mother or father or caregiver ended up learning about the topic from the child. And in this case, it was about climate change. And so we know that your outcomes, when you are combining STEM education with sustainable development, your outcomes should be social, which is intergenerational conversations. How can you educate your parents on what you've learned? How can you get your parents to move from executed actions to informed actions, to connected actions, to considered actions? And that this study proved that children do have an impact on their families.
Yes, I believe so. My son taught me a lot of
Yes.
stuff. Okay, thank you so much. Since there's no more question and we actually finish on time, so I would like to thank you for your support since last year to be here. Even you would like to come here before the COVID-19, even though we
Yes.
don't get the grant. Yeah. Thank you so much for your willingness to and your support to STEM Research Center and STEM education in Indonesia. It is greatly appreciated. And I would like to thank all participants for your very kind behaviors during the conference. It's a very fruitful discussions that we have, and it's a very, very inspiring for me as a educator how we can make impact to the society by doing these small things. Hopefully, what Dr. Carol talked about, combining the STEM education with developmental sustainability development, is really things that we should, I believe we should do that to make sure that we help our students not just academically good, but also socially, and they become a very, very productive citizens. Thank you so much, Dr. Carol O'Donnell. Hopefully we can have more collaboration in the future. Thank you for your talk. It's really inspiring.
You're welcome.
for
Thank you for
audience-
inviting me. All right.
Thank you so much. For
Bye-bye.
all audience, yeah, bye. The next talk will be from, I'm sorry, I should prepare this, but I was cut out just now. It will be, oh my God, what should I do? Sorry. Okay, the next talk will be from Professor Kichiro Kagawa from Fukui University, Japan, and with moderator Dr. Ellen Yusibani, SSEM. Thank you so much for everyone who's already here. We have 10-minute breaks, and then we will start again at 9:30. Thank you so much. I give the control to the organizer. Thank you, the technical team.
Assalamualaikum warahmatullahi wabarakatuh. Good morning. Welcome to the first STEAM virtual conference in the second day and the second keynote session series. First, let me introduce myself. My name is Elin Yushivani from Physics Department, Universitas Syah Kuala. I will be a moderator in this present keynote session. Today, we are pleased to welcome Professor Kiichiro Kagawa, a very special guest from Japan. In this session, we have 45 minutes presentation and about 5-minute question. So if you have any question, please write it down in the chat box and mention your name, affiliation, and country. The question, please be brief and clear. Okay, Professor Kagawa will present related to physics education. The title of the presentation is Frictionless Demonstration Using Fine Plastic Beads for Teaching Mechanics and Wave. It's a quite interesting theme in the physics education, mechanics and wave. And before that, I would like to brief introduction about Professor Kagawa. Professor Kagawa is a honorary professor from University of Fukui, Japan, and he got his PhD degree in physics from Kannan University. The major field research is laser-induced plasma and its application to various fields, and also he has been interested in physics education. Professor Kagawa founded non-profit organization named Fukui Science Education Academy and developed several new physics experiments since 1986. And Professor Kagawa has been engaged in the cooperative research with university and research center in Indonesia, especially Syah Kuala University. In our department, Professor Kagawa have a strong relationship with Professor Syahrul Nur, Dr. Nasrullah Idris, Dr. Kurnia Lahna, and also from chemistry department, Dr. Mulyadi Ramli. And up to that, he has published more than 150 papers on various topics in the field of laser-induced plasma, laser technology, and physics education. And now, we are welcoming Professor Kagawa. Professor, please.
Okay, my title is like this. First, I want to say about my attitude toward physics education. Several points. One point is try to use ordinary material. Don't use commercial kit, which degrade children's ability. Another one, try to encourage to have logical thinking through experiment. Okay, chapter 1 is the frictionless demonstration using fine plastic spherical beads. Introduction, mechanics is the most important to understand science technology. However, in high school, mechanics is taught through training to solve calculation problem. The most unpopular subject in high school. The reason is that due to the friction, we cannot demonstrate the law itself. And another one, for falling object, phenomena finish in a short time. Students cannot see carefully with enough understanding. This is a commercial equipment for frictionless motion. Most schools use this wheel car. But this not student cannot understand that this is a general rule. because this is special. Another way is the air slide truck. This is very nice, but only one dimension and very, very expensive. Our method is we use small, fine spherical beads. We scattered on the plane the plastic beads, and object move on the bead, but almost no energy loss because the mass, even they rotate, but very small mass. This is a microscopic view, 40 times. The size is roughly 0.3 milli and completely spherical. And we easily make the uniform linear motion. When we teach the principle of the friction equipment for children, we use a ping pong ball on the floor. Then we put a plate with a door, push, then smoothly move. Children very happy, but we notice, please confirm the ping pong ball is rotating. In Japan company, Narika, sell this kind of the beads. We put the bead on a small bottle with gaze, and on the plate, we scatter the bead like shaking paper, but almost invisible. When we take out the bead after the experiment, we use a vacuum cleaner. Usually, this bead, people say rainbow beads, because in school, this bead is scattered or it used to make artificial rainbow. Beads scattered on the black paper. Then we send the white parallel or light. Then easily we can see the rainbow. Namely the beads used as a water droplet. We published this method in physics education. This is the journal is published in England. Already 2008 we publish. But when we submit the paper, the reviewer first reject our paper. The reason is already this idea appeared in the book of Nafeel Del-Revel, but they use iron ball, 1 milli, 2 milli diameter. So rather weight. The weak point is they must use heavy object like 1 kilo, others cannot move. Only horizontal surface. If we incline, soon they fall down. Therefore, very limited application. Finally, we succeed publish our paper. The advantage of the beads method, our method, is easily obtainable object can be used, but should be right, should be flat, and very cheap, because one bottle is $50 US, one time only small amount, so very cheap. And important thing is that even slope, the bead can be attached by electrostatic force. Namely, we can make the frictionless slope. And student can systematic understanding is made, because all experiments are done using the same object on the frictionless plate. Also, students can touch the equipment by themselves as they like. Only small weak point is that in high humidity, namely on the table surface, there is a little water. Then friction increase. This is the object used for frictionless demonstration. These are Petri dish. This one is a lid of skin cream. Many things we can use, but should be flat and less 100 gram. If weight one, the friction increase. These are the frictionless plate. We construct this one. This is a little big, 183 centimeter long, 91 width, thickness is 6 centimeter. Weight is not so weight, 7.5. This one we construct using the styrofoam. Usually people use for building as thermal insulator, but rather flat and light. And this one, the smaller one, we usually use for a group experiment, 90, 60, 200. From now, I say friction plate, we call beads plate for convenience, beads plate. This big one, children can enjoy the using this bead plate, enjoy. This is the case for a PK game. There is a aim, then they try to shoot, aiming the goal. Now I want to show you a small movie. This is a small workshop for children. On the paper, there is a friction, therefore slow down and finally stop. Saigo. Okay. Next. On the bead plate, even small driving force become vivid. This move. And we put the bar magnet on the lid and put on the bead plate. Then soon rotate and this nose pole direct to the nose side. So this one high sensitive detection magnetic field. This is a compass. First, we demonstrate the first law of motion, namely uniform linear motion. Well, here, in this case, we use the aluminum disc. Diameter is 5 cm, and the only 20 gram. And this photo is taken from the top and the strobo or flashlight. Then like this, really uniform linear motion. And sometimes we use a pulse light source to record the track. In this case, 5 Hz and move, we can record using camera. This is a demonstration for circular motion. This one is a big cylindrical pipe, 30 centimeter diameter. And this is a glass petri dish. Then we start to move, then like this. We can easily see the circular motion. And this one is the cutted pipe. From here, we send the petri dish, then rotate and come out like this. Then students easily understand velocity vector of the circular motion is the tangent line. Easily understand. Now movie, short movie. Okay. And we can show the relationship between the circular motion and the simple harmonic oscillation. This is a bead plate, this is the cylindrical pipe, and we put the bright light source here, and this rotate, then we put the screen, we can see the shadow of the object. So using the projected shadow, we can show circular motion is a simple harmonic oscillation. This this move like the oscillate, like the simple harmonic oscillation. So easily understand the relation. Another circular motion we made using a string. This lid of the plastic lid, we put the pin fix. Then the end of the string we hook here. Then the lid rotate uniform circular motion. And this is a strobe light for health. If there is quite no force, the circular motion keep going on like a planet motion. Also, we can demonstrate the rotation of rigid body. This is a petri dish, smaller, middle one, the center of gravity here. Then rotate around the center of gravity, they rotate. Usually this kind of image difficult for students. Also, we can demonstrate law of conservation of angular momentum. In this case, we end of string we fix so as to be coiled around the pole. Then the string becomes short and velocity increase, like a skater spin. These are demonstration of law of inertia. We suspend the weight and move with the case on the bead plate. Then case attack on the edge. Then stop, but the weight move to forward. So easily you can see the inertia. Another one is for object at rest. This is a small bead plate. On the plate, we have a big petri dish with weight. Then one person indicates the center of the object. Another person pull suddenly, but this one don't move because no transmission of force due to no friction. This is the second law in high school textbook. If we call MA, but the student not so easy to understand. Textbook, they use wheel car. And this data was not good. Also, for a student, it is difficult to understand that this is a general law because this is a special tool. Our way, first, we show the quantitative demonstration of the second law. This is a blower. This one like sailboat. We push air, then just move. And we give force continuously with blower. The speed increase. And so easily understand. Force bring the acceleration and the speed up. Then we put the weight here, for instance, 20 gram weight. Then acceleration becomes small. Roughly, student can understand qualitatively. Next quantitative experiment is we use the pulsar on the table, and the object pulsar we pull by the constant force, namely using the weight. This is the case for 53 gram. The trace like this. That's a high acceleration. If we increase the mass, smaller acceleration. This is the data. From the previous photo, we can plot time and the velocity, how change. Completely linear. And this one small weight, this is a large weight. So easily, student can understand F equal MA. Next is the third law, namely action and reaction. In high school textbook, they use spring. But our method, we use the bead plate, we put the two magnets. This one fix, then another one come close, then by the repulsion force, this bend it. Also, this magnet also receive the force, then start to move. But actually, this is not so easy because magnet soon rotate. That's difficult to control. Therefore, we construct the circular magnet. Namely, on the petri dish, in the petri dish, we put small neodymium magnet arranged in a circular form. In this case, a plastic. We confirm the magnetic field by putting compass. This is the demonstration. Two magnets. One stay here, another one outside the same pole of magnet. Then come close, then bending. Or then this one start to move. Easily we can see that there is a action reaction. Even not touching, there is a action and reaction. This is another demonstration. We use a toy of frog. We send here, then this frog jumping. At the same time, this base pushed this way. Directly we can see the action and the reaction. Children are very happy. Also, sometime in the entrance examination of university, for a student, difficult problem appear. They say, please assume there is no friction on this surface. For instance, on the surface, another slope, and they say no friction, this no friction. When this object falls down, what happened? Well, this is difficult to have image, but we can demonstrate easily using the frictionless slope and this frictionless plate. And next is the falling object. This is the case for free falling object. The acceleration is g, 9.8, very rather large. Therefore, fall very fast. But in case of the frictionless slope, the force become mg, this case mg, this case mg sine theta. Namely, acceleration become g sine theta, become smaller. For instance, if with the 1 degree slope, acceleration become 1/60th, very small. Slowly they move with the acceleration. Also, we can measure the force directly to the slope side. This is a smooth slope. Therefore, we can measure the force, really mg sine theta. First, we demonstrate smaller mass, large mass. We fall down on the slope. We release simultaneously. Then this strobo photon. In the same way, they move, regardless of the mass, but very slowly. This is important. This one is we can make the quantitative experiment because the very slow motion, we can measure the time using the stopwatch, data stopwatch with rather high accuracy. Then we change the length and the time, this parabolic curve. From this, we can students derive time and the velocity. From this slope, they can calculate G dash. G dash means the G sine theta. They already know the theta. Therefore, they can derive the G near 9.8. This is a good practice for students. Also, we can measure the dynamic friction coefficient. For instance, we use the ground glass plate. On the ground glass plate, we scatter the bead. Then, in the same way, we measure the time and the distance. By changing the distance, we measure using stopwatch. This is the result, and this is the time and the square, distance and the time square. Then from this curve, they can calculate mu. For ground glass plate with a width 0.013, for completely smooth glass 0.001. This is a monkey hunting. This is an interesting topic in high school. Commercially, they sell to demonstrate this one. But in a short time finish, but expensive, near $400 US, and not so instructive. Our way, we use the inclined bead plate, and we use the 2 plastic lid. One becomes stone, one becomes monkey. And this stone shoot, aiming to the monkey. At the same time, monkey start to fall, but finally they attack. Regardless of speed, always attack. Very interesting, students are very happy. This is the equipment to shoot. We use only rubber band. This kind of thing also we can do. What angle gives the most far distance when we shoot with the same speed? By changing the angle, we demonstrate. So 45 cases are most far distance. Next, chapter 2. This is the horizontal spring vibration in the textbook, but the concept of this horizontal spring is difficult for students to have image. But we can easily demonstrate, but we use a little big spring connect to the petri dish. We put here the weight, then slowly vibrate. We can change the mass. So we can roughly understand this equation. Once we get to the image, for students not so difficult, but without looking at this kind of phenomena, really students have a problem. This is a non-gravity demonstration. This is an inclined bead plate. In the big petri dish, we put another petri dish with weight, and there is a plastic spring. Before falling down, a little expanded, but we release. During the falling, this spring length become natural length. No, because no gravity. Usually, slowly we can observe this kind of experiment. Also, next, collision phenomena, also important in high school. This is a case, same mass collide. This is the small one collide with a bigger one. This is a bigger one collide with smaller one. So in this case, we use the aluminum disc. This one stop here, and another one come and collide. Then this one stop, and this one start to move with the same speed. This case is a bigger one. The smaller one attack. This stop. Then this one start to move. Also, the smaller one come back. Easily, student can see. Also, in the textbook, momentum conservation for oblique collision in the textbook. So we do using the aluminum disc. This one collide, and this one come this way. This one come like this. From photo, we plot this before collision synthetic vector like this. Then after collision, synthetic vector like this. Roughly coincide. Also, interesting experiment. We can see this kind of problem in a study aid book of high school. One exists on a table, and another come another come with a speed v to collide diagonally. Prove that after collision, v1 dash, v2 dash make always the right angle after collision. This one can derive using the momentum conservation and law and energy conservation law. But we easily demonstrate. We put one and another one, shoot. Then intentionally, we don't scatter the bead around here. So this one stop due to friction, this also. And later we measure really right angle. This is also interesting. Also, important relationship between the work and the kinetic energy. On the bead plate, we measure the speed. just before, this is a paper. Once arrive the paper, there is a friction and slow down, finally stop. Then we measure the speed here, and we measure the distance. This is the equation. This is the work, friction, force, and the distance. This is work. We plot. This is the x and scale of velocity. Many times we students do, then plot, or we come in the same line. So really easily they can confirm this equation. Kinetic transfer to work. Usually difficult, this kind of experiment. Also the conversion from potential energy to kinetic energy, we fall down the object with different, we change the, then we also measure the velocity using the speed meter. We plot. This is a theory, this is an experiment. Rather good agreement. And we ask the student and in the slope, but this right part we scatter the bead. This side no bead. Ball and this petri, which one fall faster? Then usually people, students say, "Oh, ball faster." But actually, this petri is faster. This rate. Because energy consumed to rotate the ball. Sorry. Also important demonstration. We can demonstrate elastic collision and inelastic collision. In the petri dish, we put the small plastic ball loosely. Then this case is there is a cushion. Then collide and slowly collide, then come back. Come back. No energy loss because this plastic don't move. But another case, we use aluminum weight hard ball, then collide, then this ball move randomly. Then energy loss, then stop. So energy is used for thermal energy. This is a demonstration of centrifugal force and Coriolis force. This table, on the table, we scatter bead and rotate. Then come out, finally release, then we can see the Coriolis force. Now this is a movie. A little slow motion. This on friction plate, then rotate, one more. Finally, application of frictionless plate for wave demonstration. Usually, wave propagate very fast, thus it's very difficult to observe. We made slowly propagating wave using the frictionless table. This is a big white board we use as a bead plate. We scatter the beads and we put the chain of thin plastic. Plastic lead is a diameter 5 and the light, and connect using a thin rubber string. Then I show the movie. This end is a fixed, namely we can see the reflection wave at a fixed edge. Wave come, this is fixed, then reflected opposite side they come back, they move. Okay, next. This is a, no, same, sorry, stop. This case, this edge can move. Then we want to see the reflection of wave at free edge. Then come back, that's in the same phase. Okay, next. Next is the standing wave. Just fixed from this side, descent wave, like this. This is a standing wave. This is a superposed wave. Usually people use the wave machine. We show the by movie from this side, this here, we sent a wave, same phase. This opposite, sorry. This opposite case. Come back. Same phase, then increase. You skip. This from Shakuhara University, 10 students come, Faculty of Science, to Fukui, our university, to attend the international seminar under the support of Japan Monbusho. Then they enjoy the frictionless experiment. This is a questionnaire. This I will take from Fukui University student. Before demonstration, how they feel about understanding inertial law, second law, third law. After demonstration, completely they understand. Just a conclusion. We have proved that this frictionless method is very effective to teach mechanics and wave. And in order to make popular this demonstration method into educational field in Japan, our NPO, Fukui Science Education Academy, is now constructing the frictionless equipment by ourselves and trying to make donation for school in Fukui Prefecture. This acknowledgement, they support our activity. Oh, this is the frictionless plate. Now we are constructing this bigger one, and this is a small component. Thank you very much for your attention.
Okay, thank you. Professor Kagawa is very interesting. And also not so expensive equipment to doing such kind of experimental. Now I'm inviting question from the audience. Okay, I'm still waiting. So before that, I want to know, Professor, when you doing those kind of module, how much time consume for one module, for example? Because we need to arrange a schedule.
You mean the time?
Yes, to
construct?
To demonstrate maybe to the student, especially when students doing kind of work.
Not so troublesome. Not so troublesome. But flat plate, flat, then scatter the beads. And easy, very easy, not troublesome. And I hope, please, the teacher of school construct this kind of equipment Now I have a patent in Japan, but in the future I open and release the right. And now we recommend the many students to construct this.
Okay. So we can do in very short time.
Not so.
Okay. Okay, Sensei. There's also a question from Dr. Rini. How do you suggest teacher develop demonstration method in their teaching to students?
In Japan?
Yeah, maybe in Japan or Indonesia. Maybe how about your opinion?
Therefore, now we are making the guidebook together with the movie. Then maybe easily they can follow us. So we will try.
Okay.
Is it okay? By looking at the guidebook, probably easily you can do. But I hope in the future, in the textbook, they apply this method. But there are some barrier to overcome. Because we understand only the problem is that we must use beads. And sometimes people doubt the safety of beads. But we already know, no problem. Because already the beads is widely used as a rainbow beads. So no problem. I hope that in the future the textbook use our method.
Okay. We still have time. We invited question from the audience. And Professor, bead is very small, so how to recognize? Maybe we should use typical equipment, for example, maybe camera or because
You mean the accuracy?
Yeah, to demonstrate, usually use bead, but maybe those bead is small, but maybe you use a plate to see the motion or kind of that beads only supporting, but you always use maybe camera to detect the behavior.
Yeah, sometimes we use the camera, sometimes we use the video. And anyway, everything we can share because easily we can demonstrate. The student easily understand. And if this phenomenon very fast, after take a movie, we must play with slow motion. But our case, everything moves slowly. So directly a student can understand.
Okay.
Only quantitative experiment, we must use a camera or the video.
Okay, I have one question from Dr. Julkarnain Jalil from Physics Department, Universitas Syah Kuala. Wonderful presentation, Professor. In this experiment, also possible for high school students? Of course, this is for high school students. And what do you think about the using of used material for teaching aid, especially in rural area? Yeah, maybe he mentioned about used material.
Used material, what do you mean?
Not so new material. We should buy something. We just employ the material that we have in environment. It used material.
You afraid about the environment?
Material.
After we use the beads should be correct and the should be as a plastic, should be treated as a plastic.
Yeah, maybe like you use beads or you use plate. So maybe we can use the lid of bottle to replace it. It's like a used material. So you think you can use it?
Of course, no problem.
Yeah, maybe the accuracy or the purpose is
No.
can obtain by that
No,
those kind.
no problem.
Okay. Okay.
So always very cheap.
Very cheap. Okay, it's encouraging us in
Okay.
Indonesia. Okay, Professor.
I
time
hope
is
you try.
proceed to next the keynote session. So thank you again, Professor Kagawa, for answer and
Okay.
our question and also for great presentation today. It was a pleasure to have you with us. So the next
Thank you very
session is Dr. Indrawati will be moderated by Dr. Mailija. So I close the session. I want to say Alhamdulillah Rabbil Alamin and Wassalamualaikum warahmatullahi wabarakatuh.
Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Welcome everyone to the 6th keynote session of C-STEM Conference 2020. My name is Mai Lizar. I'm from Mathematics Education Department, Shah Kuala University. I'm also researcher at STEM Research Center. First of all, I would like to thank all participants for joining the session today. And I would like to thank our keynote speaker, Dr. Indrawati, who also already joined us today. Thank you, Ibu Indrawati. Some housekeeping rule for audience and participants. First, all audience will be mute during this session. If audience want to ask question, please write it down in the chat box. Please mention your name, affiliation, and your question. Now let me introduce our keynote speaker for this session. She is a very important person in Indonesia in terms of science education. Dr. Indrawati is Director of CMA Architect in Science since 2018. She earned her doctoral degree from Universitas Pendidikan Indonesia. Before serving as the director, she was the head of Program Information Department at CDTEP in Science, or what we call P4TK IPA. Ibu Indrawati started her career as a teacher in secondary school, then joined CDTEP in Science as instructor for more than 20 years. At national level, Ibu Indrawati was a member of consultant team in the development of vocational high school module in analytical chemistry. She was also a member of the developer team of Science Technology Society and the coordinator of Science National Developer Team for Bermutu program. Her research interests include science in elementary school, STEM learning, and its integration into national curriculum, managerial skill for school principal and superintendent, higher order thinking skill, pedagogical insight learning, and also about student active learning. And today, she is going to talk about implementation of STEM local content in Indonesia. So, without further ado, let us invite our speaker, Dr. Indrawati. Ibu Indra, the screen is yours. Thank you, Bu.
Thank you, Mr. Mahlidar. Good morning, ladies and gentlemen. Thank you for joining me here in this morning. Today, I represent the research team. I would like to present about the implementation of STEM local content in Indonesia. But first of all, allow me to show you a brief overview about SIGIS first. And in today's agenda, maybe as an introduction, I will show you a brief overview about SIGIS, and after that, I will present about our research, result of research. Sorry. Diklik aja. Ini itu diklik aja. Ini tolong diklik aja dari situ. Okay. Sorry to delay. Okay, ladies and gentlemen, SIKIS is destination for Syama Kitab Regional Center for Kitab in Science, established on 13 July 2009, together with another kitab, namely Kitab in Language and Kitab in Mathematics. And the institution established as a form of educational diplomacy and commitment of Indonesian government to contribute in Southeast Asia through strengthening of teachers and education personnel. And according to its mandate, SIKIS is prioritizing the competency development of teachers and education personnel in science. This task is mentioned in semi priority area in number 5 and number 7. Here you can see number 5 is revitalizing teachers education, and prioritizing number 7 is adopting of 21st century curriculum. In carrying out the mandate, SIKIS developed a capacity building for teachers and education personnel through training, seminar, workshop, and also SIKIS carry out the research and development and build networking and partnership. Here you can see the Syama Kitab in Science program and highlight. Yeah. Our training program developed is divided into regular training, in-country training, collaboration training, and also we have program C Digital Class and award for the science teachers, Ki Hajar Dewantara Award, and also we have the program International Conference, and the most important, we give the teachers and teachers a research grant. Ladies and gentlemen, STEM learning training is one of the SIKIS program. The development of STEM learning by SIKIS was initialized in 2015 under the collaboration with Academy of Technology and Engineering, Australia, ATSA, here by organizing Stellar STEM education training. And then STEM training is aimed to recognize the importance of STEM education to develop learners' 21st century skill, experience STEM lesson and activities. And also we give in the training design of and manage STEM learning activities, and also produce a STEM-based lesson plan. And then in 2018, we start to develop STEM learning to teachers nationwide under the collaboration with P4TK IPA or CDTEP in Science, and also a primary unit or directorate in Ministry of Education and Culture, and also district educational office and teachers working group. And the main theme is integrating STEM into national curriculum. In 2018, another activities of center is collaborating with teachers to conduct research on STEM integration into our national curriculum, 2013 curriculum, under the theme of improving the 21st century skill for students through STEM approach-based science learning. And from the result of 2018 STEM implementation, the main issue was limited to basic competency in curriculum and engineering design process implementation. And looking back to the former experience, and to encourage the student to be more concerned about the issue in their environment, the STEM development by SIKIS focus will be emphasized on local contact. And for the 3 years, next 3 years, SIKIS will promote, SIKIS will, SICKIS will promote the computational thinking and climate change education. Sorry. Please back. In promoting STEM learning developed by SICKIS, we have 4 strategies, namely integrating STEM into national curriculum. We suggested to the teachers to use project-based learning with focusing on engineering design process, and we also developing teachers' competence through assistance and training in working group. Here, the program teaches professional competency development to working group, and also cooperation with a policymaker, with directorate in MOE, and also in education office. And then we also publish the teachers' competency through SICKIS research grant seminar, and also we're conducting the STEM Expo. I think this is our flagship of SICKIS. As I said before, in the next 3 years, we will develop the STEM LC in this year, and computational thinking, and also CSEP. CSEP is Southeast Asian Climate Change Education Program. I think this is SICKIS STEM development at a glance. Okay, ladies and gentlemen, I will now continue to the information on STEM research on local context. As I said before, the initial program for the development of SICKIS STEM learning is to integrate STEM into the 2013 curriculum, where the identification of issues for STEM learning begins with the demand of basic competencies that can be used as opportunities to raise relevant issues and fulfill the characteristic of STEM learning. Based on lessons learned from the implementation of STEM learning through integration into our national curriculum, starting in 2019, the STEM local context was developed as an effort to optimize STEM learning opportunities to solve real problems around the immediate environment. Thus, STEM education can be used to develop the potential of students who care about their environment and can provide constructive things as citizens. In addition, through STEM local context, students can identify problems in the utilization or processing of natural resources that are abundant in their area, so that they have added value to help improve the welfare of the surrounding community. Through the local STEM context, the issues raised are more contextual, varied, and have the opportunity to practice entrepreneurial skill and have a direct impact on society through community empowerment. And the research problem here, how a teacher capable in developing lesson plan for STEM learning? And the second problem, how is the implementation of STEM learning by teachers? And the third problem, what are supporting aspects and obstacles faced by teachers in implementing STEM learning? And fourth, how are the impact of STEM learning on students? And this is the research objective. The first one for profiling the teacher's ability to develop lesson plan for STEM learning. And the second, profiling the teacher's ability to carry out STEM learning. And the third, identifying the supporting factors and obstacles faced by teachers in implementing STEM learning. And the last is identifying the impact of STEM learning on students. This research used qualitative design and a multi-case study method of STEM learning implementation. And the cases analyzed in the study were 5 classes from Bandung City and Demak District, and consisting of 2 classes from elementary school, 2 classes from junior high school, and 1 class from high school. All schools located in urban area, except 1 junior high school in coastal area with close to religious tourism destination. And the teacher characteristic here, that the teachers are key teachers who representation of their working group and have participated in the STEM local context training as preparation or adjustment for introducing STEM learning as a new approach in science learning. And the training facilitated teachers to discuss and do some activities on STEM learning, experience in developing lesson plan based on each local issues identified, do be teaching and develop action plan. And after the training, teachers are given post-training services to prepare for the implementation of STEM learning as part of their action plan in the form of mentoring. In this activity, the teacher is assisted in improving lesson plan, preparing for the implementation of STEM learning, and discussing things that need to be considered in STEM learning. And data were collected through learning observation and interview to teachers and students as the evaluation. The observation of STEM learning was recorded and conducted to time with the aim that feedback on the first learning could have improved the second learning. The interview to teacher were conducted after each observation, whilst the students were carried out after second observation. And the data collected was analyzed by 3 steps activities from Miles and Huberman, which are data reduction, data display, and drawing conclusion and verification. And from the research, we have 4 findings. The first one, the teacher was able to develop lesson plan of STEM learning with the following indicator that teachers capable of raising local issues. The local issues raised are relevant to basic competence and in the curriculum, and the teachers also capable selected the model of teaching was developed in accordance with step of engineering design process. I think this finding can be explained by the following points. One of the important characteristic of STEM learning is engineering design process as a medium for integrating aspect of science, technology, and mathematics. And but before finding number 1, I think. And STEM learning demands that the issues raised are real issues in every life, where the process of producing product as solution provide opportunities for engineering. And another explanation may be because why teachers are capable in develop lesson plan because the teacher understand the lesson plan. Another explanation is the fact that participants are co-teachers or representative of working group who have sufficient skills in carrying out their duties as teachers. A good understanding of EDP as an important feature of STEM learning make it easier for teachers to integrate EDP into the lesson plan they usually develop. And the teachers understand the lesson plan component that need to be adjusted to accommodate to accommodate ADP so that learning is carried out in accordance with the characteristic of STEM learning. And training material related to curriculum analysis, preparation of lesson plan for STEM learning, and assessment of STEM learning also strengthen teachers' understanding and skill in preparing lesson plan for STEM learning. So because the learning problem is raised from the local context where the teacher is relatively familiar with the environment, the teacher doesn't experience problem in identifying local issues that can be raised for STEM learning because they know what is going on around them. And finding number 2, here in general, STEM learning can be implemented based on step of the EDP. All teachers are relatively successful in implementing the lesson according to the lesson plan and following the EDP flow well. This possible explanation is when teacher attends STEM learning contact training, this discussion of the session on the characteristic of EDP and STEM learning material, and the discussion is carried out in detail regarding the targets, the roles of teachers and students in each stage of EDP, including discussion of things that need to be considered or anticipated. This helps teachers have an overview of the detail of STEM learning. This figure was clarified through peer teaching, reflection, and in-depth discussion, which was carried out at the end of the training. This experience, coupled with his knowledge, skill, and experience as a teacher who is actively involved in discussing and sharing in teachers' working group, and provide provision for them to carry out learning in class. Relatively intensive discussion on monitoring during the time and reflection and feedback after the first lesson strengthen their understanding comprehensively. And from observation, generally teachers face limited time constraint, especially in learning where all EDP stage is done at school, so that there is an EDP stage which is likely to be implemented less optimally. Relatively adequate time is needed in activities when students search for literature to identify relevant ideas and study the literature obtained, and also develop design, make product, and present design and trials. Another obstacle in implementing the STEM learning in class in making product, it is the availability of equipment that is inconvenient when done at school. For teachers who assign product to be made at home, the constraint for material tools and time for making product can be resolved properly. But for the implementation of activities at other EDP stages, especially teachers who decide to do all activities in class, still face constraints related to limited time allocation, so that the implementation of activity stages EDP is likely not optimal, even if the product is successfully completed. Optimization of activities at each stage of EDP is needed because when students search for literature to identify relevant ideas, study the literature obtained, develop designs, make products, and present design and trials, teachers have an excellent opportunity to facilitate skills of critical thinking, creativity, collaboration, and communication. And at the same time, students also have the opportunity to strengthen the basic concept and other supporting concepts used to develop product. If time is sufficient, the teacher has the opportunity to use it through the use of asking technique or asking a series of questions, both orally and through worksheets, so that a student can express the logical, scientific, and technical reasons behind all group decisions in developing product. The teacher can also organize classroom strategies and management to optimize the development of this skill. And finding number 3 is about the supporting factors and obstacles. Ladies and gentlemen, based on Stallman model about consideration, is about consideration here means supporting factors and obstacle for STEM learning consists for 4 aspects support. The factor are number 1 is S here is support, namely support from various parties such as the principal, teacher college, and universities, and support in the form of increased competence. And number 2, T here is teaching, which is all aspects related to STEM learning, including the ability to plan, such as compiling lesson plan and implementing learning, including assessment. And factor number 3, efficacy, which is the teacher's self-confidence in carrying out tasks, including having knowledge and skills that contribute to the information of self-efficacy, commitment, skill in planning and organizing activities. And last is M factor or material, namely the availability of adequate infrastructure for the implementation of learning. In our research here, we find all teachers in the aspect of support, all teachers receive support from the principal, teachers' peers, and education personnel. Education personnel here is a supervisor. And a possible explanation is that from the beginning, the principal has supported the teachers by allowing teachers to attend STEM local contact training and understand that the program that the teacher is participating in, so that the support has an impact on the support of other school members, such as teachers' peers and education personnel. Meanwhile, the provision of teachers to implement STEM learning was obtained by teachers when they attended training and post-training services in the form of assistance during the preparation for implementing STEM learning, which was carried out relatively intensively both through social media and face-to-face before the first and second observation. And in the teaching aspect, provision in planning and implementing STEM learning are obtained through STEM local contact training. Based on the explanation in the implementation of STEM learning above, the competencies obtained through training can relatively help teachers to carry out STEM learning, even though teachers face obstacles at different stages of EDP. And in the aspect of efficacy, when teachers attend training, no instruments are distributed to determine the contribution of content and pedagogical knowledge to the formation of self-efficacy. Given the importance of the role of self-efficacy as one of the factors that need to be considered for implementing STEM learning, this measurement needs to be done during training so that it can be followed up if strengthening is needed to increase this self-efficacy. Teachers' commitment can be seen from the completion of tasks from during training and after training. And in the material aspect, school infrastructure is adequate for completing the product. The obstacle faced by teachers were the lack of strong and stable internet access and the difficulty of bringing the equipment for making processed seafood product to school. The obstacle here faced by teacher number 1 in Demak district. And the funding number 4 is about the impact on students. STEM learning implementation gives impact on student improvement in terms of concept understanding, forces, skills, entrepreneurship, interest, positive responses on learning activities. Here, teacher 4 even measure the impact of learning on student activity. This response so that students have an interest in following STEM learning. According to the definition proposed by Wahagio, that interest is a condition in which a person pay attention to an object accompanied by a feeling of pleasure because it is considered to have benefit. And sorry. And also that STEM learning can increase student interest, stated by Shahali et al. Here. In the STEM field and career in the STEM field, that interest of the student will ultimately increase the student literacy of student, as stated by B also, knowledge, attitude, and skill to identify question and problem in life situation, explain the natural and design world, and draw evidence-based conclusion about STEM-related issues. From our response from teachers number 1, number 2, and number 4, they measure that STEM learning improve learning outcome, even though the end-gain result of teachers 1 and 4 are in the moderate category. The impact of learning outcome is supported by the result of research by Swarma and Enda in 2015, which state that STEM learning can increase motivation and creation in learning science and increase student understanding of concept. Other research shows that students who carry out project-based STEM learning show higher scores on the concept being taught, and then those who carry out project-based learning alone. And in general, teachers stated that STEM learning facilitates the development of problem-solving skills. In STEM learning, the form of task is relatively open so that students must be more independent in completing them. Teachers must function themselves as facilitators so that the inquiry process can be carried out by students properly. The success of students in completing assignments shows that STEM learning can facilitate the development of problem-solving skill. And we find from the teacher number 5 also found that critical thinking, creative thinking, collaboration, and communication skill improve. This shows that the EDP stage, which provided opportunities to develop these 4 skills in advance, has been successfully utilized by the teachers. And another impact that was measured by teacher number 1, who raised issues related to the economy, was the increased entrepreneurial interest of students, which became added value. This shows that there are opportunities for teachers to use STEM learning to provide added value to students according to the issues raised and the local context issues, local context use. And from our finding, let's review the key point from the research. So from the research, we can conclude that number 1, the teacher were able to develop a lesson plan, which indicated by the ability to identify local issues for STEM learning and to implement the engineering design process or ADP as one of the characteristics of STEM learning that can integrate concepts to solve local issues has been illustrated in the lesson plan. And the second conclusion is teachers are relatively able to implement STEM learning according to the lesson plans, and the teachers facilitate students so that they are able to carry out EDP relatively independently. And number 3, our conclusion is teachers receive a good support from school principal and peers in the form of permission to adjust learning schedule and technical support during the implementation of STEM learning. And the last, that the student gave positive responses, and STEM learning implementation can improve their ability to solve problems, improve policies skills, and increase the student achievement. And from our research, we recommended the following. Based on the time constraint faced by teacher, it is necessary to consider alternative to implementing STEM learning as a school project or part of the youth scientific group program, which can provide more time and a more flexible schedule. And if it will be integrated into the intracurricular system, it is necessary to comprehensively organize the time allocation, including the layout of the learning schedule and the daily lesson schedule. If you need additional time but do not allow it to be used as homework, consider carrying out assignment at school outside of class hours. For elementary school level, it is necessary to consider using a special time allocation for integrated learning or project that are usually available at the end of each sub-theme. And based on time constraint and access to information, especially at the basic level, it is this their mistake. Ladies and gentlemen, and the recommendation. I said the recommendation. Yes. Okay. The recommendation. Okay. Thank you. Yes, the recommendation number 2, the teachers are suggested to provide more varied information sources for students so they can have a chance to hone a skill to selecting and sorting out needed information. And the next recommendation, considering the importance of self-efficacy in STEM learning implementation, teachers' training should measure teachers' self-efficacy, which can be done by providing concept and pedagogical content knowledge enhancement. I think that is all my presentation about our research. Thank you.
Ibu Indrawati for very interesting, insightful presentation. Now we got about 10 minutes for question and answer. The first question from with Artika. The question is, in further research, what aspect of efficacy that do you think is critical to be observed from the teacher while doing the learning process, and how this aspect might relate to the improvement of students in 4C skills? So you got the question, book?
Yes, may I catch the question? What critical aspect when doing the next research?
Yes.
This is the point?
Yes. What aspect of efficacy for the next research to be crucial to be observed?
Oh yes, I think for the, if you if you're interested implementing a STEM lesson, the critical aspect that you have considered is the content knowledge and pedagogical content knowledge, how to facilitate students in activities on EDP. It is very important. And why the aspect of content knowledge must be mastered? Because many, not many, I think from our experience, teachers almost forget to raise the prior knowledge, and student cannot use the science concept and math concept to solve the problem. If the student have what I mean, not good, but in the mastery of concept is adequate. I think it's easier to teachers to give the student or not to guide the student to choose the solution. And it is the important thing when the student in the first stage of EDP, after identified the problem, they have to give the solution for the problem. I think this the critical aspect is content knowledge and how to guide the student in each stage on EDP.
Okay, thank you very much for the response. We got another question from Nana Diana from Universitas Pendidikan Indonesia. Thank you for the nice explanation, Dr. Indrawati. Well, I wrote the literature about teachers' difficulties in implementing STEM in Indonesia. Based on the result, both Indonesian mathematics and science teachers share common difficulties in implementing STEM, which is low understanding about STEM, lack of facilities, and limited time provided in the teaching schedule due to the demanding the curriculum content. So I would like to ask a question. Are there any practical solutions to overcome these difficulties? Okay, yes.
Okay. Okay, thank you for the questions. As mentioned before, that the teacher difficult in Indonesia to implement the STEM learning is one of the factors is the lack of time allocation, and also maybe facilities. And for this, I suggest, based on the constraint phase of teachers, maybe science teachers and math teachers can collaboration among another teachers. Science and math can collaborate among them, and maybe can make a team to implement the STEM. And here we suggest it is necessary to consider alternative to implementing STEM learning as a school project or part of the youth scientific group program. Maybe in Indonesia is called kelompok kerja ilmiah, and maybe it will be integrated into the extra curricular. In last year, I also invited team in one school to attend our training. Consists of science teachers, math teachers, and ICT teachers, and also language teachers as a teamwork to do the STEM learning project at school. I think that is my suggestion about the how to implement this STEM learning in our condition.
Okay. All right, thank you very much, Bu. So we got the last question here from Pak Faisal Manurung, Universitas Asahan. The question is, how STEM start to learning by bringing up local issue in our materials? Yes, that's the question. Do you want me to repeat it?
How to start?
Yes.
May repeat, please?
How STEM start to learning by bringing up local issue in our materials? Maybe how to bring local material to, local issue to the material of STEM, maybe.
Yes.
Yes.
Oh, yeah. Okay. Maybe the first teachers have to identify what the issues in their environment. It is very important. Why we choose the STEM local context, because if if the local context issues is raised in the classroom, teachers have know what's going on in their environment. So it is make easier to teachers to enhance or to guide a student to identify the problem. So how STEM start here? Maybe the first is teachers must identify the issues in local context first, and then identify the basic competency in the curriculum, which one related to the issues, and develop the material. In our experience, the local issues is all can connect with our basic competencies. Here need teacher skill to what we call this to develop the learning material, include the worksheet and another media. I think it's my answer.
Okay, thank you very much, Bu. Time is up. Let me wrap up our session today. I think Bu Indra already present very interesting topic today. First of all, about strategy of STEM implementation by SEAKIS. I think this is very important, so the audience will understand about this strategy. And the second one, the importance of local contact for STEM integration, and also the importance of teacher collaboration. Again, thank you very much, Bu Indrawati, and thank you very much for our audience.
Thank you.
And for the next session,
Thank you. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh. For the next session, it starts at 11:30. Our next keynote speaker is Professor Nasir Mansur from Exeter University, the United Kingdom. And this session will be moderated by Dr. Wiwit Artika. Thank you very much for your attention for this session. Assalamualaikum warahmatullahi wabarakatuh.
Assalamualaikum warahmatullahi wabarakatuh. In the name of Allah, the Beneficent, the merciful praise is done to Allah subhanahu wa ta'ala. Because of him, we can gather in good situation and condition. Salawat and salam may praise to our beloved Prophet, Muhammad sallallahu alaihi wasallam, who is really loved by Allah and has guided us to choose the best choice of the way life. Good afternoon, ladies and gentlemen. My name is Wiwit Artika. I'm a lecturer from FKIP Unsia from Biology Department. It is my honor to be a moderator for this fourth session of the keynote. And I would like to appreciate and thank you so much for Prof. Nasir Mansur that I heard from the committee who have been attend very earlier in this morning. Okay, ladies and gentlemen, first of all, may I briefly introduce you to our keynote speaker from United Kingdom. So Prof. Dr. Nasir Mansur is a professor in science education, Graduate School of Education at University of Exeter, United Kingdom. He has been recognized and promoted by Supreme of University in Egypt to full professor in science education at Tenta University. He is also a member of Distinguished Contribution to Research Award Committee for National Association for Research in Science Teaching. He also served as editorial board for international journal published in English or Arabic, the editor-in-chief for Social Science and Humanities Open Journal, and an associate editor for Thinking Skill and Creativity. Professor Mansur has a research interest in aspects of teaching and learning in science, including the STS, curriculum studies, inquiry-based learning and teaching, controversial issue, scientific literacy, STEM, creative thinking in science, and teaching about nature of science. He also interested in multicultural studies in science education, also the communication technology, ICT, and 21st century skills. So, ladies and gentlemen, without further ado, I would like to please Prof. Mansur to proceed the talk in 50 minutes with the topic S in STEM education and school science, from science capital to STEM capital. So, Prof. Mansur, time and place are yours. Thank you so much. You can proceed.
Thank you so much for this kind introduction, but I would like to thank you also for inviting me for this conference, which is focused on a very, very important topic, and it's a very timely topic for Indonesia and for all the world. So thanks for addressing this important issue. But also, I would like to thank so much the organizers for this conference. Doing it virtually is not easy at all, especially you have a big number of presenters and the keynotes, but you have done a brilliant job and a wonderful job and outstanding communication. So makes our life very easy virtually. Even now, a minute ago, I got a reminder about this keynote. So thanks so much for that. Okay, I will share my screen with you to just start the presentation, and hopefully this will work well. Okay. Just to make sure, can you see the presentation?
Yes, it's very clear.
It's very clear. Yeah, the topic today is on S in STEM. S stands for science. So I'm talking about S in STEM, science education and school science. And we will see what is the difference in this presentation. But also I'm going to argue about what is the capital, what is science capital, and what is STEM capital, and how can we move from science capital to STEM capital. Okay, where I'm located in Southwest in England, in UK, and coming from Exeter University, which is one of the top universities in UK, and we have a wonderful city. We hope that we welcome you soon to Exeter here. And this is my interest, just in case if you want to get in contact and we can have a network and work together, because this is the purpose of this academia and this conference. Okay, what I'm going to focus on. What is the key argument for me today? One argument is to have STEM school culture, and this will require collaboration among stakeholders and building this kind of collaborative and supportive STEM community. But we have to understand that there are many factors and the agents that can facilitate or hinder the integration of STEM in the current science education. And we have to capitalize on the factors that can facilitate the integration of the STEM in the current science education. So we will aim to help developing this kind of science capital, and you will hear from me a lot today about the science capital and STEM capital. So develop the the science capital through engagement in school science, which in turn supports the development of students 21st century. And that is the outcome we hope to end or for the science curriculum or for the science education to help us with. Okay, what I'm going to focus on today. One thing, I'm going to present, of course, something about what STEM education is, but also the key ideas about developing the STEM curriculum through answering the key questions: what is the science capital and what is the STEM capital, and how can we capitalize on the science through STEM resources available in schools. But also, it's not just the school, it's about the community we live in. In this presentation, I will also argue critically the relationship between science capital, STEM capital, and STEM culture, and the cultural and the human capital. And we will see how can we put the three capitals together to create this STEM culture. Okay. From science to science in society. As we try to build STEM culture in school, the first thing we need to understand, what is science? What is the nature of science that we are promoting? And who is developing this science? Are we contributing to this science as a community of, for example, British community, American community, Indonesian community? So who is contributing to this science, and how can we address this in the science curriculum? So this is quite important, which is part of the history of science. And when we understand what is science we are going to deliver or want to deliver, of course, we will answer the question, what is science education for? And if we put both together, what is science and what is science education for, we will come up to the question is, what should the science curriculum will look like? Answering all these questions will help us to start to think about who is delivering, of course, the teacher. And we'll start to think about the science teacher education in service and pre-service. Okay, so there are three things we need to think about. Of course, science. And of course, we hope to do a STEM career and STEM culture and STEM capital. But we live in a society and we are human. We build history, we have culture. So putting these three together, that will be very important to have this STEM culture. And that's what I will focus heavily today on my presentation, about the relationship between these three, addressing these three. Okay, I will start with the science capital. Science capital is a concept that can help us to understand why some young people have a science identity and why some other don't have this science identity. Why a young children age maybe 11 or 12 say, oh, science for me. I think as a scientist, I would like to study science in the future. That's when we call this, yes, we have a science capital and we have a science identity. When you have science identity at that age, we can ensure, and that will ensure to us that in future, this child might have career in STEM or might like to continue studying in STEM. So developing this kind of science capital to have attitude about science and to study in science, knowledge about science, thinking scientifically, that will help us to have these students or these kids to continue studying in STEM disciplines. So science capital here, we can define it in four aspects, or have four aspects here. What you know. So this is about knowledge of science, but also about how you think about what you know. And what you do. So you know, and you have kind of scientific thinking, but what are you doing with this? What are you doing with science when you are in your kitchen? What are you doing in science when you go and to be a customer to buy a TV or something like that? So our behavior in our society, our practice in our society, and who you know as scientists, current scientists or the scientists in the past. So who do you know? So if you put all these four aspects together, that will make science capital. And we need to consider these aspects when we come to think about the curriculum and think about the pedagogy, as we will talk. Okay. Moving to the STEM capital here. So STEM capital, that is the knowledge and social contacts, attitude, skill, experiences that a student or a person has, and how those resources inform their engagement and choices in schools. Thinking about career in science, having a career in science and thinking about a career in science or STEM, that might help me engaging with the activities in the schools. So STEM has this kind of a mission that all students, that's what we hope, all students for further education in science, technology, and mathematics, to prepare them to take career in science or in STEM. Allow all students access to career in these fields and to prepare all the students for the opportunities of the future. And we will talk more about that in a minute. Okay, so what is science and what STEM education? So answering these questions, and when we look at all these pictures, we can see science. We have science in the lab, we have science in what we eat. As we are networking now, this happens through science, science in beauty, makeup, and things like that. So we are surrounded by science, but this is the community we live in. This is the career we are dealing with. So to do this and live in this society, that is the relationship between the science capital and the STEM capital. STEM career, STEM opportunities, STEM society, STEM culture, and that's what we are hoping. And we hope that the science curriculum will address all these issues considering the society. Okay. When we have a child going to the school in Indonesia or going to the school in United Kingdom, we find kind of differences because there are differences between these two students in terms of the culture. So students in the journey between home and the school is carrying many of their culture and elements of this society, and this has to be considered. What do we have in our society? What do we have in our community to bring to the school? So we are opening channels between the schools and the communities. And so our resources, our human resources in our communities. So, and that's what we call science identity. So science identity is dealing with us in terms of history, in terms of gender, in terms of history, and that will make our identity identical, is different, unique, from a society to society, a country to country. So contextualizing science is quite important in our science curriculum. STEM capital and culture borders. So when you look at society like Indonesia, for example, what do you have in Indonesia? What do you have in Jakarta? How can you connect science and the schools to your community? Universities we have, how can we connect the university we are giving this conference today in to the schools? How can we communicate the outcome of this conference to our schools? So that is what we call STEM culture. What do we have in a community? What do we have in the industry? What do we have in terms of informal science education? Museums in Indonesia, museums in Jakarta, and that's what we call culture. And that's how we can develop the STEM and science capital in the schools. So science or science education has to consider this kind of the beliefs we have about our culture, about science, about STEM. So this needs to be considered when we think about the science education. So our stereotypes about science education is quite important, and sometimes these stereotypes about science and scientists might put some students off to study science and might help students to take science as a career in the future or STEM related career in the future. So, and that again needs to be considered in the science curriculum and in the science education and in the science pedagogy when we are dealing with our scientific issues. Okay, I will give you one example about this culture. Okay, thinking, for example, about our sociocultural context, what's made of for a teacher, all right? And what I'm saying to a teacher about teacher can be applied to students. So we have in service training, and we have out school life for a teacher and students. We have a school, we have universities, but also we have our own religious beliefs. If we put all these together, that will make the teaching experience, and they can also make the student experience. So we have interpretation of this experience, and that will influence on how we teach. Or how can we learn science? And based on that, we have our constraints, we have identity. So we can have science identity, student identity, teacher identity, and that will develop our knowledge. And this is just one example about how our culture capital and the human capital and our culture interact with what we deliver in the school or what is already in our community. And that again needs to be considered when we teach science and learn science. And sometimes we have false contradiction between, for example, Islam, for example, and science. But any element of culture, we might have false contradiction. And that again needs to be considered when we think about the science curriculum, so considering again the human capital and the cultural capital, it's quite important. Contextualizing, have a context of the science and the context of the STEM we are delivering. This is quite important. You cannot impart, for example, if something working well in America and something working well in United Kingdom, you cannot easily say, all right, it works there, it will work for us in Indonesia, it will work for us maybe somewhere else. The context is quite important. Our culture is quite important. Okay, give you another important thing about addressing the culture and addressing the human capital for us, which is important to give a model for science students to see our great science. What did they do? And it's part of the history. Who is developing the history of science, and this is part of the nature of science. If I'm asking now the audience about, and I'm not expecting an answer at the moment, but I always say it when I'm in person, how many Muslim scientists do you know? Who can count 5 Muslim scientists? Say anything about even one scientist. Honestly, when I done that 2 years ago in Jakarta, when I was there, in the Islamic State University, I didn't get much. And when I done it in Saudi Arabia last year in Riyadh, in a conference there, I didn't get many. But if I convert the question to ask about how many Western scientists do you know, we will find lots of people are putting their hands up, because the curriculum we have is very Westernized. I have no problem to open to look at the culture of other and to look at the science curriculum from other countries, because at the end of the day we teach science. But it's important as part of the science and as part of the pedagogy of the science education is to give model, and this model should come from our community, and it comes also from the other, addressing the history of science very, very well. So this is quite important. I'll give you an example here. We have hundreds and hundreds and hundreds of Muslim scientists. Okay, giving just an example here, you get Razi, and if I'm giving a presentation about the history of science and the history of the Muslim scientists, we will have hours. Okay, Nisina did a lot. You give is the Zahrawi. So we did a lot in medicine, in math, in many things we did. Okay, so and you will have this presentation and you will look at it. Looking at here, for example, as we are talking about science, Jabir ibn Hayyan, father of the chemistry. Who knows Jabir ibn Hayyan in Indonesia or in UK or in somewhere else? How the Western science is addressing our culture and celebrating our culture. If they don't do, we should do it, because that will help the science capital, that will help the STEM capital, that will give free models for our kids and the Muslim community and the non-Muslim community as well. That by itself can create a peace. Science can create a peace between the West and others. Okay, so major books written by him. Many books written by Jabir ibn Hayyan, Book of Kingdom here. He's done lots of things in chemistry. Talking about chemistry, who knows about his contribution in about discovering nitric, hydrochloric, and but also in terms of STEM, crystallization, and lots of things about preparation of various metals. So he's done a lot in STEM. So STEM is something not new for us. No, it's not new for us. It's been there for centuries, but we need to address that. Okay, gaps in STEM now. When we look at the future, if we look at the left side of the slide, the life and the future of STEM, what do we expect? 75 or more of jobs will be in STEM. Okay. And not just STEM careers, it is STEM in every job. Even when you go to cut your hair, when you do your makeup, whatever you want to do in the community is in STEM and needs a STEM job. Okay, business and the industry, they want STEM. But when you look at what we have here, and after the 5th grade in elementary, we lose interest in STEM and science by 25%. And when students move in school, we lose another 15. So we lost now about 60%. And when they move to the secondary education, we lose another 15% of the students interested in science and the STEM. That means the outcome will be 25%. Who are going maybe to have to continue in STEM discipline. And that's not enough for our need, as we need 75%. So there is a gap here between the outcome of science and the outcome and the need of the society or the expectation of the STEM career. Okay. How can we capitalize on STEM resources, and how can we address this in our curriculum and science education? First of all, I have to highlight that we need to start very early. STEM is not something you will address it in higher education. When we have engineering or when we have medical schools, is something needs to happen very early in preschool, in elementary, and in middle school. So this kind of continuum contribution of the science curriculum and the STEM curriculum, science capital and STEM capital needs to happen very early. So our STEM vision and our STEM aims needs to happen in this continuum, okay? Another thing which will help, which I started my presentation with, is opening the school to our community. Knowing your human capital, knowing your resources in your community. So if you are in Jakarta, for example, when you teach something on recycle, how is this happening in Jakarta? Okay, and that needs to be addressed. And if it's happening in another city like Malang, for example, how can I address this? So having this kind of local problems about water and things like that needs to be addressed locally, but also what's happening globally, internationally about this problem. So real world problems we need to work on. Communication about this problem we need to work on. So this is one thing. But also, if we think about STEM pedagogy, STEM lesson, STEM curriculum, we might need to address the STEM standards. What are they? What is the practice of STEM? First, we need to have rigorous science. So if we're teaching science, STEM, so science in STEM, so we need to capitalize on STEM, the facts of STEM, of science, the theory of science, the nature of science in STEM. But also, I will say the same about math. So we have to have this kind of rigorous discipline, okay? Integrate science, technology, engineering, and the mathematics content, but also interpret and communicate STEM information, engage in inquiry. So we need to have hands-on thinking scientifically, and I will come back to the inquiry in a minute. Engage in a logical reasoning and thinking, collaborate as a STEM team, apply technology if we can. When we have these 7 elements, we can take these 7 elements and we can say, all right, how many elements of these 7 can we include today in our lesson? You don't have to have the 7 elements in one lesson or in one unit, but you can have a rubric, for example, to be able to address this maybe over a unit or over a course of a curriculum. This is another example here about engaging or addressing the STEM culture in school. So I found the next generation science standard quite engaging, especially when it comes about inquiry and the design, learning through design and learning through inquiry. But also when we look at the disciplinary, so they are capitalized in science. So what we need to do more, and which is missing from this one, is capitalize in our culture. You cannot take the next generation science standards and applying in Indonesia as it is. So the culture capital is quite important, and that's what's missing in this. If we are imparting this, or if we are integrating this in our community. This is another example here about engaging in the elementary. So you get the student, you get the learning environment, you get the standards, but also you get at the end of the slide here the global issues and the local issues. And that's what we need to have in mind when we are developing the unit for teaching science or have a science curriculum. This is coming from our research in Saudi Arabia. We done this project, and we were studying the views of science teachers about STEM and how can we integrate them and the challenges they have about the integration of STEM, and moving from science teaching to integrating STEM teaching. And we found that we have to have two cultures here, school culture, but also the partnership culture. So you have to build a community inside your school, in the school, but also to open this school and to cooperate with the industry around you and with the resources around you to be able to move from the science or pure science to have integrated STEM. So we need to think about that when we and address this when we have the curriculum. I'm going to move on because maybe the time will be kind of ending soon here. Integrated STEM curriculum here. Very quick, 7 elements to integrate the STEM curriculum here. Project-based learning, based on real problem, based on global problem, based on local problem. So we have to come in the year and say, all right, what is the problem we have today in Indonesia? Around the world, how can we address that? How can we connect local problem to a global problem? And that will address the in and out school, museums we have, and so on, the activities that is going every day. How can we bring this to the school? What's happening in the newspaper today? How can we address that? Like the pandemic we have, how many of us communicated the pandemic issue and the stereotypes about the pandemic we have now to the food we are eating, and to how the science is addressing this, how the science is addressing this. How are we thinking about this pandemic? This needs to happen very early. As we're asking students to put mask on, why do we have to put mask on? How can we argue that from the science background? Integration of technology and virtual learning, and I think we are addressing this all in the school now. Assessment need to be changed. Considering assessment for learning needs to be changing. What we are expecting from STEM need to be reflected on our model of assessments. Our professional development need to be different. When I'm preparing a teacher to teach science is different from preparing the same teacher to teach STEM issues. So that need to be considered, but also on formal science education. How can I prepare teacher to be able to communicate with the museum and to bring the museum to the school and take the school to the museum? That needs to be, teacher needs to have a training about that. Outreach is quite important to listen to the future of the student. The future of the student is the community, is the industry, is the needs of the society. So we need to update us in the science curriculum about that. But all of that will be kind of a communication, and to have this kind of business and schools, universities, and all of that need to be ongoing engagement in a communication. When we do that, we will end with a STEM student who will be able to help us in the future. He will be able to, when he goes to the museum, will not be just amused by the entertainments that in the museum. He will think about the museum and engage in the museum with his science hat on, okay? But also thinking about business and all this stuff. So that's when we end with STEM. So this is a puzzle we need to sort out to have a STEM culture. But missing one element of this puzzle will create a gap in the STEM culture. So we need to put things together, assessment, community, our vision nationally and internationally, and that will help us. This is kind of what we have addressed today. It's a message for all of us, for our science educators, but also for our research. We need to think about this kind of science capital, STEM capital, human capital. How can we address this? Place-based education. We talked about that today. How can we address this in our research and in our science education? Context-based teaching, career in STEM, environmental education, science-based economic skills. Science should help with the economy and should have some solutions of that. But you have to prepare your kids to be able to communicate, to be able to help you in your economy and understand what the industry needs and expected from them. Okay, I'm going to maybe have a 1 minute or 2 minutes just to give an example about how can we put that as a lesson, all right? And how can we put this in a classroom? A very simple idea here. First of all, we need to have a free space. By a free space, we mean everyone is free to think, to express idea. You need to have this kind of open space for dialogue and inquiry. So you need to allow your students to talk and you listen to them. So you have a ground rule, no one left out, good atmosphere, and they need to think, but also, which is very important, teachers don't have all the answers. All right. So how can we prepare for that? This is kind of, we make them ready. So how can we make the student focused? So you have to bring in, and first of all, here, so there are 6 elements we will consider in a lesson when we prepare a STEM lesson, for example. First of all, we say, here, looking at perspective. So you need to think about the perspective, about an image, about a film, about a cartoon, about song, about story, something to get the attention of the student, to make them focus in relation to what you are going to teach. For example, here, I'm teaching something about a designer baby, for example. We have concerns in terms of religion, in terms of culture about that. But also we have concerns from the science background. But how can we communicate that? So we can bring this image to the student so they can reflect, they can think, they can bring their cultural thoughts about it, their science thoughts about it. And we can think about, yes, big ideas about and the big concepts about genetic disease, specific physical genetic traits, and all this stuff. But the image or film will make them focus and get their attention. And after that, we can say, all right, what do you think are the strongest arguments for the gene selection, for example? If we like to make a gene selection, What is the key argument here? Is it the parents' needs? Is it the cultural argument? Is it the religious argument, the scientific argument? What is the key argument? In this case, you let the student express their thoughts. Drawing, writing, make them write ideas down, draw ideas down, share their ideas with each other. Then make questions in birds. Which ideas we are going to explore today? And when they are voting on this question, they will start to argue, debate, bringing the culture, bring their understanding of science, bringing the capital of science, sharing ideas, exchanging views, and exchanging ideas, shifting views. It may be sorting out stereotypes by this kind of dialogue, thinking about it, sharing these ideas. So this is kind of these 7 elements, moving from broad to sharing ideas, to have a dialogue in a very open space, in a very safe space, having this kind of cultural views, cultural perspective, that will help the teacher to sort some misconception about science, some misconception about religious, some misconception about stereotypes about culture. And this is quite important. And this is a big rule for our science education, not just to deliver science. I'm going now to end this by asking the host. I have a video, very nice video, showing a teacher how it's challenging their students, but also having this kind of a space, environment, free environment, free space of dialogue, free space of interaction, changing the type of assessment. And I think that is what we need when we are delivering science and STEM capital. So could you please put these videos on, please? It's a very short one. It's maybe 3 minutes or 4 minutes. So it's quite short, but it's quite interesting. Do we have it with us, the video?
Well, let me ask you another question. How often do you think about things that happen outside of this town? You watch the news? Yes? No? All right, so we're not global thinkers yet, but why aren't we?
Because we're 11.
Good point. What's your name?
Trevor.
Maybe Trevor is absolutely right. Why should we think about the world? I mean, after all, what does the world expect of us?
Expect.
Mm-hmm. Of you. What does the world expect of you?
Nothing.
Nothing. My God, boys and girls, he's absolutely right. Nothing. I mean, here you are. You can't drive. You can't vote. You can't even go to the bathroom without a pass from me. You're stuck right here in the 7th grade. But not forever. Because one day, you'll be free. All right, but what if on that day you're free, you haven't prepared, you're not ready, and then you look around you and you don't like what the world is? What if the world is just a big disappointment?
We're screwed.
Unless you take the things that you don't like about this world and you flip them upside down right on their ass. Don't tell your parents I used that word. And you can start that today. This is your assignment. Extra credit. It goes on all year long. Now, wait a minute. What? What's wrong with this? What's the matter? Yes?
It's like so...
So what? There must be a word to finish that sentence. Someone help her?
Weird. Crazy.
Weird. Crazy.
Hard. Bummer.
Bummer. Hard. How about possible. It's possible. The realm of possibility exists where? In each of you. Here. So you can do it. You can surprise us. It's up to you. Or you can just sit back and let it atrophy. Atrophy. If there is a word you hear that you don't understand, there's a dictionary at the front of the room. Look it up. And there are these dictionaries which you will carry with you at all times, because in this class, we're going to learn to love words and their meanings. Any questions?
Yeah. So you'll like flunk us if we don't change the world.
Well, no, I wouldn't do that. But you might just squeak by with a C.
What you ever do to change the world?
Well, Trevor, I get a good night's sleep. I eat a hearty breakfast. I show up on time. And then I pass the buck to you. Now, I want you all to write your names in these books. And what's your name? Molly. All right, I want Molly to look up the word atrophy.
Okay, thank you for putting this video for us. I would like to thank you for giving me the opportunity to talk to you today. But also, I wish that after this conference, we get together and we build a kind of a network, and then we can work together in terms publication, research projects. I would like to see what is coming out of this conference. It's not just a conference that we present, it's a conference that we know each other, we get to know each other. So I hope that will be a following up activities from through the year. So if this is the first conference, and from a year to year, what is happening? What do you want from us, and how can we engage with each other? Thank you so much.
Okay, if you said so, maybe later I will not hesitate anymore to contact you for further collaboration, Prof. Okay, thank you very much for really incredible talks here from Professor Mansur. It is like you pack like all the information that I have learned during my 3 years doctorate program courses in one day. You connect all everything is about natural science curriculum, and then also philosophy and how it is related to the STEM capital and science capital. So okay, I would like to read a question from our audience. The first question is from Sir Michelle Wallan. So she's our international student from Africa. From Africa, if I'm not mistaken. So the question is, what are the yardsticks for the students to contribute within the industry environment while still in the tertiary stage using the STEM policy? So what are the yardsticks for the student? Yes.
What is what?
What is the yardstick for the student to contribute? Yeah, within the industry environment. Yeah.
Do you mean the student in as grade 12, grade 10, a student in a class, a student in a school?
Yeah, in the stage of tertiary stage. I guess maybe it is in elementary school. Yeah,
okay.
Using the STEM policy.
Thanks. This is quite good question. It's quite important question. When we were young, back in Egypt, we used to visit kind of some industries around us, industries that maybe have something about Pepsi, Coca-Cola, and things like that. And it's quite nice to prepare students before they visit the industry, to give them an introduction about this industry. What do we expect to see in the industry? What kind of questions they might want to ask? And when they come back to the school, what did they say in the industry? Can they, for example, here we are thinking last week, I mean, the students about this kind of a problem about pollution in water, all right, and pollution in air. And you are visiting industry that you might think that is causing a problem to the community about pollution. A simple question to engage the student with when they are in industry, they can engage with the people there. What do you do? What is your policy in your industry? Or what do you expect from us? Do you have a job from us in the future? What kind of job do you have from us? I think this such a simple activity, simple questions and simple interaction that will create kind of a memory that will stay for forever. But if we have more memories of that, more visits of that, more industry of that, that will create this kind of a STEM profile, a STEM desire, a STEM culture inside the student. Will not think about science, it's just a homework, it's just a science teacher and a science book and a science class. No, it's beyond that. There is a real science waiting for us to take part of or serving us. So this kind of appreciation between science and scientists and the industries, and this is quite important. This is a very, very, very strong message that we want to have it in the science curriculum and in science education.
All right, thank you, Prof. I hope you are satisfied with the answer, Mike. Yeah, because he is one of my students in the international based class. All right, Prof, there's a question. What the title of the movie is looking so inspiring? Some of audience asking about the title of the movie.
Yeah, I have it here somewhere, so I will send you the title of this. It's quite interesting. And I always like to put this, even you can use it in the training, when you train teachers, and to get them think, and even ask the students, what do you think about this environment? Ask the student voice. You can make a research by just this video to get the student voice, the trainer voice, the teacher voice. It's quite stimulating, a very nice one. But yes, I will send it to you.
Okay, so for the audience, you should be patient. Yeah, we will tell you later. Yeah. Okay, and then the next question is from Bapak Faisal Manurung from University Asahan. Previously, I was very interested in topic presented, something that STEM curriculum is not supported by the local community. What is the solution to this problem? And how to design STEM curriculum in higher education? So it is like he thinks that STEM curriculum is not supported by the local community. What do you think about this? What is the solution? And then how to design the STEM curriculum for the higher education? There are two questions, Prof.
About the first question about no interest from the community or local community about supporting the science curriculum. First of all, we have to ask, it's the same like the problem between, or the issue about the egg and the chicken. Who comes first? And who should have the solution for that? Who should have a communication for that? The community and STEM career is losing face about the ability of the science curriculum to help them. They think that the science education we have now does not have the skills they are expecting, all right? The local community don't know how to communicate their needs to be addressed in the science curriculum and in the science education. So there is that channel between the community and the school is blocked somewhere, and it's always top down or top bottom kind of communication. Whatever the Minister of Education is interested in, that will be happened. Whatever comes in the media, that will be happened. So I think we shouldn't blame the local community for their lack of engagement and communication with us, but we should have a start. We should put some efforts. Start small. Start with what you know. Don't lose hopes or confidence about that. But I would say the local community and local industry, they are in need for your help, for your skills, for something like that. But the problem is in us, in our curriculum. Our curriculum is very dry. It's very dry. We don't have real issues. How many times we heard Jakarta when we teach science education? How many? How many we heard Indonesia when we teach science education? How many scientists, Indonesian scientists, in the science curricula? So make your science education local before you ask the local to be science. So I think the start is from us, addressing us. Ask them to visit you. Get a fireman to visit you, a policeman to visit you, a hairdresser to visit you. Appreciate the jobs. Not just to put medical jobs, engineering jobs as this kind of top jobs. Hairdresser and people who are making makeup, any jobs should be appreciated and should be celebrated, because our point in science, this is something related to science. Back to the question about higher education and how can we do this in higher education. There are many ways to do this in higher education. Always at any and most of the universities in the world, you get the School of Education is in one part out of the campus, out of university, has no contacts with the schools of sciences, department of physics, department of chemistry. So they are not communicating with each other. And so that's one issue. But also, we don't have STEM activities in our higher education. STEM programs in our higher education. Do we have masters in STEM? Do we have CPD, continuing professional development in STEM? So we need to celebrate from time to time the STEM vision, to be able to have this kind of STEM culture in higher education, opening the universities to the local community again. This is quite important, and that will create the STEM culture. Yeah.
All right. Thank you, Prof. Hopefully, Pak Faisal is satisfied with the answer. Actually, there's one short question, one more question. I'm worried that the participant will be disappointed if I don't ask this question.
No, please go ahead.
So, yeah, what do you think about the STEM approach? Yeah, the implementation of STEM in social science, because so far she heard that a lot of STEM is only related to technology and then math, physics, and how about in business, history, and social and other social expertise? Yeah,
this is absolutely great question, and I'm sorry that I didn't highlight that in my presentation. Interdisciplinary is not just about science, technology, engineering, mathematics. it is science can be when we talk about history of science, when we talk about geography, we are talking about science. So you can make connection between different disciplines. If, for example, there are now a call for STEAM, science, technology, engineering, A for art, and the science. So it's very important to make a connection not just between science and math. You can make connection between science and geography, science and history, science and literature, and science and English. So this is quite important. But everyone has expertise in something, and that's why I'm calling for a STEM culture in the school. How can different departments can help each other to create this kind? When you have an issue about water, for example, pollution in water, here you need a science, but also you need a math. You need somebody from a geography department, somebody from sociology. How can you communicate this to the society and things like that? So you can have an issue, for example, if you have a spider map, for example, put it in the middle and you start to say how science contribute to this, how geography contribute to this, how sociology contribute to this, and you will be amazed by the contribution that it comes from different disciplines.
All right, thank you, Prof. We have reached at the end of this session. Yeah, so I can conclude that how to build a STEM capital is very important to students to connect the science in school to their society and their surroundings, which is also influenced by the school culture and partnership culture. Once again, thank you, Prof, for your attendance in this conference and your incredible talks. And thank you for the participants for your attention. Assalamualaikum warahmatullahi wabarakatuh.
Thanks so much for you, and thanks for all of you.